Hello, everyone. Oh boy. All right, I think that's enough to get started. Enough viewers. Um, First of all, I made some throwing knives yesterday, and I have to say, this is like the most pleasing shape for a throw. Actually, maybe for any knife. Like, just that is a pretty cool shape, if you ask me. It's very ergonomic. Probably the favorite shape that I've made in any knife that I've made so far. I just really like the shape. Too bad this is junk steel. Like literally the first time I threw it into the target, well, I didn't throw this one, but I threw another one. It goes thunk, and then because of its weight, it sticks into the target. But then because of its weight, it keeps carrying. It has momentum, and so that puts a lot of torque on the tip, right? Because you throw it, it sticks, but the rest of the knife keeps going, and it bends the tip. Um, so if it wasn't junk steel, then it wouldn't bend the tip. But because it is junk steel, it uh, all right. So today we're going to talk about electric field lines. So this is CHL 24 period 7. Okay, so what are electric field lines? Basically, electric field lines are a picture of the electric field pattern due to some charges. Okay, so that's all it is really, is it's a picture. Now you can make electric field lines with you can make an electric field lines with a computer, in which case your picture is exact or very close to being exact. But we're just going to sort of freehand draw them. So all it is an approximate picture. All right. And so it's a way of getting an idea of what is happening with the electric field without doing any math whatsoever. So this lesson has no math. It's just all approximate sketches that give us an idea of what the electric field is doing. Okay? And so there are some rules. So I'm going to teach you the rules for drawing electric field lines. So the most basic electric field line pattern is to have a single positive charge plus 1. Okay? And so the way that the electric field lines point is they just point directly away from a positive charge. They just point directly away like that. Okay? Now here's the thing. You get to decide, you get to choose how many lines corresponds to a plus 1 charge. Okay? So, and that basically determines the level of detail of your picture. So, all right. So in this case, I'm choosing 4 lines for plus 1, a charge of plus 1. Okay. If I wanted to be less detailed, I could choose 3 lines for plus 1. If I wanted to be more detailed, I could choose 10 lines for plus 1. I don't know. It doesn't. So you pick the number of lines that plus 1 is going to have. All right. So now what if I had a plus 2 charge? Well, plus 2 is going to have twice as many lines as plus 1. So it's going to follow the same pattern of the lines going directly away. Okay. But there's going to be twice as many lines going. Okay. And if this was a charge of plus 3, it would be 3 times as many lines going away. All right. So the number of lines is related to the size of the charge. Okay? But so you get to, however many you want plus 1 to be, you do you, okay? But once you choose how much plus 1 is going to be, then all the other amounts of charges have a fixed number of lines. Okay? Now, what if we had a minus 1 charge? Okay? So a minus 1 charge is going to have the same pattern as a plus 1 charge, but the difference is that the field lines are now going in. Okay, so field lines go away from positive charge, and they go toward negative charge. All right. So let's talk a little bit about interpreting the electric field line. Okay. Now remember, the formula for electric field due to a single charge is KQ over R squared. Okay. So the way we interpret the electric field lines is that the concentration of lines is basically the strength of the electric field. Okay, so what we see here is that what happens as we go closer to a charge. See how the lines they start out far apart, and the closer you get to the charge, the lines come together. So that's a reflection of the fact that as you get closer to the charge, the electric field gets stronger, which is represented by this 1 over r squared factor, okay? So the concentration of lines is related to the strength of the electric field. And furthermore, we can see why we have to double the number of lines if we have twice as much charge, okay? Because if we double the number of lines, then we're going to have twice the concentration of lines. And we can see here that if we increase the amount of charge, the electric field gets stronger, okay? So this interpretation is consistent with Coulomb's law. The other interpretation is that the electric field points tangent to the lines. Okay, so right here, the electric field points tangent to the line, down. Right here, the electric field points tangent to the line, up. Right here, it points tangent to the line, away. Okay, so it points tangent along the field line. Okay, so that's how we interpret the picture that we draw. So these are all just like one charge by itself alone in the universe. But what if we have more than one charge? Okay. Now here's the thing. If we have, so let's say I have a +1 charge and a +1 charge. So first thing you want to do if you have multiple charges that are interacting with each other is you want to try to identify lines of symmetry. So what are different ways, what are different lines of symmetry? So in particular, right here is a line of symmetry, because if I take a +1 charge and a +1 charge and I reflect it about that line, I still have a +1 charge and a +1 charge. Okay? So that's a line of symmetry. It's symmetric to flipping like this. Furthermore, we have a line of symmetry right here. Okay, so if I take this and I flip it like that, I still have the same configuration of charges. So, you know, electric field lines, they're always going to respect the symmetry of the charge distribution, okay? So, you know, a tip is to identify lines of symmetry. All right, that's a tip for you. Now, if we think about this one, it's got, this charge has a field line that goes out, this charge has a field line that goes out. So these charges, or these field lines, are on a collision course. But here's the thing, field lines cannot cross. If field lines look like they're going to cross, they have to bend to avoid each other, okay? So what they're going to do in this case is they're going to bend maybe like this. Okay. So field lines cannot cross. They bend to avoid crossing. Okay. So, and then they have a direction, so I want to make sure to include the direction. So they would do that. Now, once I've done that, I have this line of symmetry, so it has to do the same thing below that line. So they're going to go down like this. Okay. And then I'll draw just a couple more lines that sort of do the same pattern. So what I have here, because this +1 charge has 5 lines, so this is a different system than this picture, because here I had 1 charge is 4 lines. So this is +1 equals 5 lines. Okay. So now the next obvious question is, what happens if we have a positive next to a negative? All right. So what if we had a positive +1 next to a -1? All right. So in this case, this charge has a field line that's going out. This charge has a field line that's going in. So what happens is, when you have opposite charges next to each other, is the field lines link up, like so. And this field line is going out, this field line is going in, so the field lines will link up. And obviously this one has a line of symmetry this way. So they will link up like so. Draw a couple more. These field lines are linking up. All right. Kind of looks like metaphase plate from cell division. Remember metaphase plate from cell division. You got your prophase and your metaphase and your anaphase and your telophase. This is metaphase plate. That's what I always think of when I see this. Okay, so these are the two most important patterns: is a positive next to a positive and a positive next to a negative. All right. Now, how does and by the way, one of the things you notice is that this does not have a plane of symmetry through the middle. And the reason is if we flip it, now we have the negative on the left-hand side. So that would reverse the direction of the electric field lines. Okay. So what if we have a +2 next to a -1? All right. We have a +2 next to a -1. So this does not have a line of symmetry down the middle, because to flip it would, oh, this is supposed to be a +1, my bad. Because then we would have the +1 on the left side instead of on the right side, okay? But it does have this line of symmetry, because if we flip it like that, the charge distribution is unchanged. So if we think about this, the field line is going out. The field line is going out. Okay. Now, if you have a positive charge, a large positive charge next to a small positive charge, its field lines are dominant. Okay, which means that they're kind of like stiffer. All right. So instead of right here, because of this line of symmetry, they're equally balanced and they go straight up. Here they're not equally balanced, and this one is gonna, the +2's field lines are gonna kind of push into +1 territory. They're gonna be like, domination, ah, okay. So they push into the +1 territory. And then the +1 has weak field lines, so its field lines are just going to yield. They're just going to be like, like that. Okay, so they just kind of give up. They're just like, I can't combat this +2 charge. It's too powerful. So what you can see here is I have 5 lines for my +1, so I better have 10 lines for my plus 2. So I have to do 6 more lines. So I'll do 3 on the top and 3 on the bottom. So now that looks pretty good. Okay. What if we had a plus 2 next to a minus 1? So in this case, again, you have a similar situation where the plus 2's field lines are going to really push into minus 1 territory, okay, because it's a larger size charge. And then they kind of tend to loop around back almost. So they'll do something like this. And this field line will go out and kind of back and loop around. Back and loop around. Okay. And so here I have 4 lines for a minus 1 charge, so I have to do 8 lines for the plus 2. So I'll do a couple more lines, just going. Okay. So what we've learned here is that big charges have lines that dominate little charges. Okay. Now, one of the things you can see is that if you have an equal amount of positive and negative charges, you're going to have the same number of lines going out as you have going in. Okay, because this system has a net charge of 0 because it's plus 1 minus 1. It's a net charge of 0. So that means that every line that goes out ends up on a negative charge. Okay? But here in this drawing, I have a net charge of plus 2. So that's not 0. All right? So where do these lines go? You know, I drew them as just stopping, but field lines never stop unless it's on a charge. Okay? So what these lines do is they just continue out forever and ever. Okay? So lines either end on a charge or go to infinity. Okay? This is related to net charge of the system. Okay? So basically, so for example, this system right here has a net charge of plus 2 minus 1. So this one has a charge of, this system has a net charge. So for this one right here, Q net is plus 1. So therefore, it's going to have 1 charge's worth of lines going out to infinity. Okay, because there's an excess of 4 lines that have to go somewhere. Okay, so these 4 lines are all going out to infinity because there were too many positive lines for the amount of negative charge. Okay, so that means 4 lines to infinity. Here we had a net charge of plus 2. So that means we get 2 charges worth of lines going out to infinity. Here we have a net charge of 3, so we have 3 charges worth of lines going out to infinity. Here we have a net charge of 0, so we have no lines going out to infinity. Okay? So if there's not enough spaces for a line to end on a negative charge, it will just go out to infinity instead. PU, Hazel. All right. So what we're going to do now is we're just going to do a couple of examples, okay? So what if we have more than two charges? Let's suppose we have a +3, and then we have a -1, and then we have a -1. Oh, excellent question. So Geography Genius asked a question about what if you have two negative charges next to each other, and it would look identical to this, but the lines would be going in instead of going out. Okay. Okay, so what we're going to do for this one is we're going to notice that we have a line of symmetry right here. Okay, so for that line of symmetry, that means that if I take my electric field pattern and I flip it like this, it had better look the same. Okay. And then another thing I notice is that this system has a net charge of +1, right? Because +3 -1 -1 is +1. So what that means is that I'm going to have one charge worth of lines going out to infinity, and the rest should curl around and end on negative charges, okay? So what do I see here? I see a plus next to a minus. So that's going to make a metaphase plate. And because it's imbalanced, the +3's lines are going to dominate the -1. So you have something like this, and then maybe a like that, kind of dominating. Okay, now I have to draw something symmetrical on the other side of this pattern. Okay, and here I have a minus next to a minus. Okay, so if you have a minus next to a minus, remember it does the thing, just like plus next to a plus, except if it's minus next to a minus. So plus next to a plus, it's whoosh. Minus next to minus, it's whoosh, like that. So these guys are going to have lines that go like this. But here's the thing. These lines can't come in from infinity. All right? So they have to loop around. So they're going to go off the page, and circle back around and go like that. Okay, like so. And then maybe I'll do another one going like this, and then so those two lines correspond. Then I can even complete that one. Okay, so now let's see what I have here. I've got 4 lines for this -1 charge, and I have 4 lines for this -1 charge. So that means this +3 has to have 12 lines. Okay. So currently this one has 8. So I've got to draw 4 more. And so I'm just going to draw, and they all go away from this +3 charge. So I'm going to, a lot of times electric field lines will follow these lines of symmetry. So I'm going to just draw one that goes like that, one that goes, and then I'll draw 2 more going up like this. So that's an idea of what that electric field pattern might look like. It's just approximate, okay? What if I had a square of +1 charges? All right. So this is going to have a lot of lines going out to infinity because the system has a net charge of +1. Okay. And furthermore, it has a lot of lines of symmetry. So we've got a line of symmetry right here. We've got a line of symmetry right here. We've got a line of symmetry right here. And we got a line of symmetry right here. So there's a lot of symmetry in this problem. Okay, so I can see +1 and +1, so that's going to do the thing. So these two have a fill in that goes like that. But then, because of the symmetry, I have to draw this like all over the place. So I go, and then, okay. And then I could draw some more lines if I wanted to. I could, I don't know, maybe do this, and then just repeat that. And maybe I just want to stop there, because then I say +1 has 4 lines. So I have 16 lines going out to infinity. All right. Now you might ask the question, well, why didn't I draw any lines going into the middle? Okay. And the reason is, what if I drew one line going towards the middle or something? Then that would mean that I would have to draw 4 lines going towards the middle. So all these lines are headed towards the middle, okay? And they can't cross. And furthermore, they can't link up because these are all positive charges, okay? So there's basically no way for all these lines to avoid themselves. So basically, there's not enough space for all the lines to avoid each other if they all went in towards the middle, so they all just kind of go out. So what that translates to is, remember when we interpret the electric field line pattern, the concentration of lines is related to the strength of the electric field. And so because this region doesn't have any electric field lines, that means that the electric field is very weak there. It's approximately 0 there. Okay? And that's pretty easy to understand why. Imagine if you were like at this location here. You are getting pulled or pushed. Let's say, for example, we put a negative charge right there. This negative charge is going to get pulled in 4 different directions in such a way that it almost cancels out. Okay? So, yeah. We'll do one more. Let's say we have a charge of +2. And then we have a charge of -1. And then we have a charge of +1. And we have a charge of -2. Okay, so this system has no lines of symmetry. Okay, so what we do is we just kind of start drawing. Okay, so I see a positive next to a negative here, so I'm going to do like a metaphase plate kind of thing. Okay. And here I have a positive next to a negative, so we're going to do a metaphase plate thing. This is the bigger charge, so its field lines are going to be dominant. Like so. So this -2 charges lines are going to push into +1 territory. Put the direction of the lines here. Okay. Here I have a positive next to a negative. So again, I have metaphase plate with this one's lines being more dominant. So maybe a like that. Okay. And then here I have a positive and a negative. So maybe these field lines might connect like this. All right. So let's see where I'm at here. I've got a +1 charge has this +1 charge has 4 lines. 1, 2, 3, 4. Okay. This negative one has 4 lines. 1, 2, 3, 4. So these +2 and -2 each has to have 4 lines coming out of it or going into it. Furthermore, the net charge of this system is equal to 0, right? Because +2, -2, +1, -1. So what that means is that no lines to infinity. All right. So what that means is that all these, the 4 additional lines that come out of this +2 have to get taken up by the +1, or the -2, excuse me. So I'm just going to draw them. 1, 2, 3. You might even have one that goes around like this. 4. Okay. So there you have it. There's a representation of the electric field pattern. Okay. So, and again, we want to remember how to interpret it. The electric field points tangent to the line. Okay. And the strength of the electric field is related to the concentration of field lines. So like over here, the electric field is going to be very weak. Kind of in this region, it's going to be strong, etc. All right, so, excuse me. What would happen? So one of the things I told you the other day is that if you are an electric charge, you create an electric field, but you don't feel your own electric field. You move in response to the electric field due to everything else in the universe. Okay? So you're moving around in response to all the other stuff in the universe. Okay? So we could imagine, what if these charges are all the other stuff in the universe? Okay? And what if I put a positive charge right here, for example? What's going to be the direction of the force on that positive charge? So this positive charge is going to move in response to the electric field due to everything else. That's a good question. What if a +1 is surrounded by a bunch of other pluses? Then you are going to have an extremely messy electric field pattern. It's going to be really messy. Okay, so this positive charge, remember positive charges get pushed. Positive charge is pushed along the electric field. Negative is going to get pushed against. Okay? So this positive charge is going to get pushed along the electric field. So the force on this positive charge is going to be here in that direction. All right? What if I put the positive charge here instead? The force is going to be along the electric field, but here I'm going to draw a longer force arrow because the concentration of lines at this location is larger. What if I put a negative charge right here? Negative charges get pushed against the electric field line, so it's going to get a force that points in this direction. And I drew it a small force arrow because this region of space doesn't have a lot of field lines. Okay, so that's how it works. Now you might be tempted to say that this plus charge, for example, is going to follow the field line exactly and end up right here. That's not true, okay? Because what will happen is that this positive charge is going to get accelerated. It's going to pick up speed, and as it picks up speed, that means that basically that the electrical force can't turn it fast enough. So it tries to follow the field line, but as it picks up speed, it kind of gets its momentum makes it kind of not follow it exactly. So it might do something like that in response. And this one will probably do something like this. So it'll kind of start to bend, but it won't be able to because it's going too fast. So let me write that down. Charges won't follow the field lines exactly. All right. So there you have it. So I have good news for you. Because this isn't really a quantitative lesson, it's more qualitative. There is no assignment for this lesson. So there's just only one quiz this week. And then because next week, yes, it is like escape velocity and gravity. And actually, we could draw gravitational field lines if we wanted to. So just like there's electric field lines, there's gravitational field lines. Gravitational field lines are more boring, though, because all of the, you could basically imagine that gravitational field lines, because there's only mass, there's not positive mass and negative mass, all the field lines have this kind of a pattern, okay? Because you don't have equal and opposite masses to make the metaphase plate, okay? So anyways, what we're going to do is we're going to go to the Zoom room, and I have a couple of web applets that I'm going to share with you guys that will